All right, now we're going. All right, can you guys see the slideshow at this point? Can someone just give me an audio yes or no?
Yes,
Yep,
I can.
we can see it.
Okay, great, thanks. All right, so Carnot mapping, or what we'll call K mapping, is basically another process of finding ways to reduce minterms. Okay, except instead of using Boolean algebra to reduce it, we can use basically a visual kind of graphical format to do reductions. Okay, so you can kind of see from the picture here by finding groupings that have similar logic, okay, but have maybe like one term that is different or overlaps, that we can find reductions that way. So um, the limitation of K mapping is that it works well for 2, 3, and 4 input systems, but once you start getting bigger than that, then it doesn't quite carry over. Okay, but I prefer it heavily to Boolean. I think you will as well once you get the gist of it. So okay, this is just kind of what I said, graphical technique. Okay. All right, so basically, it's called the K-map because, as you can see here, what they've done is we have mapped out the final outcomes of a truth table. You can see on the left side and the top that we have the input terms. For example, this would be a 3-input K-map. They're using A, B, and C for the particular inputs of this one, but the letters, can change, obviously. Okay. It's maybe hard to see here quickly, but it is kind of in an order that is mostly sequential, starting with, our all switches off at 0, okay, A naught, B naught, C naught, and then progressing through 1, 2, 3, 4, 5, 6, 7. Okay. All right. Apologize if this is a little bit off. This was converted from Microsoft to Google, so things might be shifted. So different ways that we can simplify. Okay, basically, we want to make groups wherever possible. Okay, groupings can be done vertically or horizontally. They don't really work diagonally. Can't do that. But we are able to reduce. Let me move some of these things out of the way. I think they're covering up the info. Sorry. All right, this is getting a little bit covered up here. But basically, here we have two separate terms, okay, in this particular map here. This one represents not W, not X, and this one down here represents W, not X, okay? Using K-mapping, what we could do is actually group these two ones, okay? And that would actually reduce, we can hopefully see the Boolean reduction, right? We have a not W into W, and that would cancel out, okay? It would reduce down to a 1, and we basically be left with just not X, all right? You can kind of see it. My mouse doesn't cover it up. Yeah, at the bottom of the screen, hard to see, it's getting cut off, but there is a not X that would reduce, okay? All right. So this is kind of how the K-map is going to lay out. It's pretty easy for the 2-input one. You can see 0 goes in the upper left-hand corner. Number 1 goes here, 2, 3, okay. And that would, again, align with our counting. Okay, remember on the left-hand side here, we're basically counting in binary. So we've got 0, 0, okay, and that's the output column. We've got 1, that's the output, 2, okay, and then 1 and 1, 3, and that's the output.
These are kind of like Mendel kind of things.
Yeah, it kind of is like that. Yeah, like the
Punnett squares.
Yeah, the Punnett square. Yep, in a sense it is. Okay, and you can see a little animation here. So we're assigning those outcomes to the actual map here. Okay. So these are just the different ways that you could group. Okay, you could group an individual, although there's no reduction. Okay, groups of 2. All right, we can go both vertically and horizontally. A group of 4, but in this case, that would mean basically that it's always on. So there's really no logic to it. But these same groupings apply to bigger maps. So when we go to the 8 input, or we go to the when we go to a 3 or 4 input system, then the 4 would be a possibility. Okay, whenever possible, you want to make the biggest group you can, because the bigger the group, the better the reduction. Okay, so more groups, less groups that are bigger is better than more groups that are smaller. Okay, all right. We're going to jump over that because I think it just makes more sense to see it play out. Okay. All right, so here's an example that they give. All right, again, going down, we would map out, okay, the first one here, the second one here, 0 and 0. Okay, the original terms would have been not J, not K, and then not J, K. And again, we can see basically if you look at the map, the term that both numbers share in common is the term that will remain. So basically, in this case here, not J is shared by this one and this one. And so if we group them, then not J is what remains, and K and not K will cancel each other out. The same would be true in a group of 4, okay, although you're going to have 2 letters that overlap in the groups, and then 1 will reduce away. We doing okay so far? Can someone give me an audio yes?
Yeah.
Okay.
Yes, sir.
Thank you. All right, so here is an example of the 3-input map. Okay. So one tricky thing about this one is that if you notice at the bottom of the map here, positions or counts number 4 and 5 are at the bottom, and 6 and 7 are in the 3rd row. So that means that these 2 over here are actually going at the bottom, and these last 2 are actually going in the 3rd row. The reason for that is that in order for the K-mapping reduction to work correctly, we cannot change more than one variable on each step, basically in our little table here, our map. Okay, in the truth table, it follows our binary count, but what would happen is that in the 3rd row here, we can't change not W to W and X to not X at the same time. That would be too many changes at once, and they would actually be too far apart for the reductions to happen. Okay, so in that sense, we just have to kind of flip them around like that. Okay, it's a little tricky, but I think once you get in the habit of doing it. Okay, so again, watch the animation here. It's going to go to the bottom 2 and then to the middle 2. Okay, and I should actually, I do have some templates made up that actually have these little numbers in them. So when you're doing this work, you can actually, you can hopefully not forget to switch these around. Okay. All right, so just another look too at different types of groupings that we get to have in here. So here's groups of 2, okay, going throughout. Groups of 2 vertically we could have going throughout, okay, both in the middle and the ends. I wish some of these would go away. We can actually have what we call a wraparound group. So you can see that it's capturing the top left one here and the bottom left one down here. So those 2 could be a group, because if you look, they actually both have not C in common. They both have not B in common. And then it's A and not A is what changes. So they're actually only one term apart. Okay, same thing can happen this way as well. Group of 4, so this would be better than 2 groups of 2. This would actually reduce down to a single term. A group of 2 would reduce down to 2 min-terms instead of 3. Okay, so it'd be less reduced. Box of 4, great. Box of 4 in the middle, but box of 4 on the top. Okay, wrap around of 4, so 2 on the top, 2 on the bottom. Okay, also can work. All right, group of 8, again, if this is the case, then it's always on, and there's not really any logic involved. But okay, so I'm going to break out of the presentation here for a second, because what I want to do is do this one on our own here. Oh boy, sorry, here we go. Okay. So if you have a separate piece of paper, I would recommend that you just kind of follow along with me quickly here. All right, so again, first what I'm going to do is just kind of label where the different outputs are going to go. So this is the 0 spot, 1, 2, 3. Again, jump down for 4 and 5. and then 6 and 7 go here. And whenever I'm doing these, I like to, on my paper, I'll draw the lines every 2, just so I don't get mixed up. It's very easy when you're staring at all these 1s and 0s all over the place to mix them up and put them in the wrong spot. So, okay, and then so now basically 0, okay, goes here. All right, this 1 here, 1, 0. Again, these are going to have to jump down, so it's actually 0, and this 1 is going here, and then 1 and 0. Okay. All right, so does anybody see some groupings? Oh, and actually, I'm sorry, before I go further, let's also write out what the terms should be on the side. So, and this is important because otherwise you're going to get the wrong logic terms. So it should be not E and not F here. And then we always start with the not, oops, sorry, that's a G, not G here, and then G over here. Okay, again, if we're following the truth table, then F turns on, so we've got not E and F here. All right, again, this layer here, we're actually jumping way down here, so that's E on and F on. And then finally, way down here, we're going to be back in this row, so it's E on and F off. Okay. All right, so now does anybody see some obvious groups that we should circle and then reduce?
2 and 6.
You're talking about rows 2 and 6. Can you describe it on the map for me? Oh, 2 and 6.
Oh,
Oh,
the
okay.
numbers.
Yeah, I see what you're saying. Okay, positions 2 and 6. Yeah, so we have a group right here. Okay. How about, is there another grouping that we can do? So we would also have this wraparound group from the top right and the bottom right. Okay. So again, from here, in order to figure out what the terms are, it's whatever letters are in common. Those are the ones that we keep. So in this one here, they both are not G, and they both are F. So this would reduce down to F and not G. Okay, these are going to be separated by an OR. And then the other group here is going to reduce down to G and not F. Okay, and that would be our updated statement. We would have had otherwise 1, 2, 3, 4 terms with 3 letters each, and we reduced it down to a statement of 2 groups with 2 letters. So that's quite a savings right there. Okay. And there they go. They got the same answer that we did. Great. Okay. So let me go back to this. Oh. Everybody doing okay at home still? Did we catch following along? Yeah? Anybody sleeping yet? All right, so all right, so here is what a 4-input K-map would be looking like. Okay, so at this point, remember, we have 16 possible outcomes, okay, 0 through 15. So the really tricky thing in this one is that, like the 3-input K-map, these 2 rows are going to be switched, but also these 2 columns are also going to switch for the same reason, right? We can only have one variable change, so it gets a little squirrely here. So again, you definitely got to pay attention to where they all go. It's nice here that they have it marked out for you. And what I like to do again is draw a line. In this case here, I'll draw a line every 4 in the output column, just so again I can track where I am and not make mistakes as I'm laying out the map. Okay. All right, so here's their first row again. So, going in order here, it goes 0, 1, 2. So basically it goes here, 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 and then to the third spot. Okay. 1, 1, 0, 1, jump back. Now we're going to jump way down to the bottom row, but still do the pattern going left to right. Okay, and then the final one there. Okay, lots of different groupings here. So a lot of these are going to look like similar from the other ones. So we've got, wrap around with 2 and 2. Okay, it can happen in the middle. It can happen on the sides. It's hard to see this one. I think you can actually get the 4 corners is a possibility. Okay, so here we've got another wraparound with rows top and bottom, sides. Again, if we got this one, then they're all on. They didn't show in here too, any boxes of groups of 4. So, a group here, group in the middle, group on the side. Okay, there's lots of possibilities in this big one. So again, I'm going to escape out of this one. And let's jump and try to do our own example here. Okay. All right, so again, first let's start by, I'm going to label all the boxes. Again, on a piece of paper if you can. I would recommend that you follow along. So 0, 1, again, 2 goes out here, 3 here, 4, 5, 6, 7. Way down at the bottom now, 8, 9, 10, 11. Oh, I messed that up actually. Sorry. Should be out here, 10, and then 11. And then finally 12, 13, 14 on the far end, and then 15 back in the third row. Okay. And again, in my output column for my truth table, I would really recommend 1, 2, 3, 4 that you draw a line every 4th one. 1, 2, 3, 4. There we go. Okay. Just again, kind of visually help you to track stuff. Okay, and now let's start laying in the 1s and 0s. So 0, 1, 0 on the outside, and then 1, 0, 1, 1, 1. Again, this row member going down here. Okay, so 0, 1, 0, 0. And then finally 1, 0, 1, 1. Okay. And now let's just write in all of our min-terms on the side here. Again, starting with these 2 on the right. So it's not R, not S. Okay, then S turns on. So it's going to be not R, S. Then RS, which again, remember, is really down here. And then finally R, not S. All right, and a similar thing going across the top, except with TU. So both off to begin with, not T, not U. And then U turns on, so not T, U. TU, remember, because we actually had to switch. And then finally T, not U. Okay. And does anybody see any clear groups right off the bat here? Box on the right. Could someone want to chop on the microphone and try to describe here? It's okay to be wrong. Jimmy McGooey, what do you think? Do you see some groups here?
I see that group of 4 in the middle on the top 2 rows.
Okay, right up here. Yeah, I agree. There's a group here, 4. Good. I see another group of 4 in here too. So something that we might not have seen before, but it's okay for groups to overlap. So believe it or not, there is another
group. Another group, Mr. Kish. Oh, you're circling it.
There we go. Another group of 4 right there. Okay. Any other spots where we might be able to get a smaller group that overlaps?
12 and 14.
12 and 14. Yep, that can work. So we got a wraparound group here. Good. And there's one more in there.
And then the wraparound from the bottom to the top.
Yeah, we got 9 and we got 1 here. So yeah, there's quite a bit of overlapping in here, and that's okay. If you have to overlap in order to make a group where otherwise you may not have been able to make a group, then that's a good move. Overlapping to make groups for no reason, there's no need to do that. For example, it would not make sense to add another group and say, oh, there's another group of 2 here and another group of 2 here. Okay, that actually isn't helping you. You're just making more terms and you're not actually reducing. So again, the biggest groups possible. Overlapping is okay if it helps make a group, but it's unnecessary to just overlap just to get more groups. Less groups is better if possible. Okay. So now let's go ahead and write out the terms then. So let's do the big ones first. Okay, so this one here, again, we have the overlapping letters. So it would be, in this case here, S on the side and T on the top. So it would reduce to ST. Okay, this second big group would reduce to not R and U. Okay, and then we have our small group. So in this one here, since it only got 2 numbers, 2 ones there, it's going to be 3 terms. So it's got not R, RS in common, and then it also has not U in common. So that's going to be RS, not U. Okay, that was this one. And then finally, this one here in the middle. So R, not S. So not S is in common for those 2, and then not TU. So that'll be not S, not TU. And that was that group. Sorry, I know it's a little messy here. Okay. And we can check our work down here. And I think we nailed it. Everybody doing okay with that so far? Does that make some sense? All right, last little bit. We're almost done here, okay? All right, so the only other thing that we look at K-maps is that there are some conditions that we call a don't care condition, which in the K-map can be marked, or in the truth table can be marked by an X. So this is basically a situation where that particular output doesn't matter for the design that we're doing, okay? Maybe we're integrating 2 bigger systems, thinking about like an automobile. We've got lots of sensing systems in there, so maybe the sensor is feeding in, but in this particular case, we don't really care what happens because it's not, even though it's integrated into the bigger system, it's not really important for that particular part of our design, okay? So in the truth table, you may see an X, okay? And then as a result, in the K-map, we would put an X in place of a 1 or a 0. And again, just basically means we don't really care what the output of it is in this particular thing. But if you see it in the K-map, okay, we basically then can group the X with a 1 if it helps us to reduce, okay? If it doesn't help us to reduce, then we just leave it alone and we don't actually count it towards a midterm, okay? So for example, down here, I'm not going to make us map this whole one out again. Let's just scroll down to the answer here and take a look, okay? So basically, they used these 2 X's. You can see the X's over here in the truth table. And then they used these 2 here, okay, to make a group of 4, which was great. They used this one down here to make another group of 4. And you can see the other ones here, they just kind of left alone, okay? So they didn't have to count them. It only helped, okay? Again, we had this group of 4, so it wouldn't make sense for us to say, oh, well, here's a group, okay? Because now we're just adding overlapping that doesn't really help us. It would create another term that would just make the equation longer, okay? And there's no need to group 2 X's together. Again, we don't really care that they're there, so there's no need to include them in terms for 2 X's. All right. All right, and that really brings us to the end there.